We're finally ready to start multivariable calculus, which means from here on out, in any real problem that we are encountering, we should have enough dimensions available to describe the three space dimensions of the problem, the potential time dimension of the problem, and in theoretical physics, for example, potentially other dimensions in the more abstract models that theoretical physics provides. Now, the main adjustment that we're going to come about will be a visualization adjustment, and that can be surprisingly tough at times, even though I hope that the transition will be smooth here. The other adjustment will be that every so often computations will be a little bit longer, but on a positive note, if we're looking at multivariable calculus, basically multivariable calculus really is not that bad as long as you can visualize the objects and as long as the computations don't bother you. Well, okay, great. Neither of these tasks is trivial, so I'm telling you something here that basically says if you can do stuff that's really, really difficult, then putting it together isn't going to feel that hard. But we are at the stage now where we ought to be able to make that transition, and well, let's see what we can do with it. Basically, there will be a constant interplay between the visualizations and the computations. And so especially early in the course, we will look at visual tools and how they connect to computational entities like equations. So if you're looking at what we have up here, coordinates, points, spheres, equations, that's all stuff that you do very early on in pre-calculus also. And what we're going to see here is in some ways a review and a comparison between what we are very familiar with in 2 dimensions and how it scales up to 3 dimensions as well as to higher dimensions. Okay, so the biggest immediate jump that we're going to see right away is as we're going from 2 dimensions to 3 dimensions. And well, let's see how that goes. In 2 dimensions, we have coordinates that connect geometry and algebra, and right? And that's the old, very familiar situation that if we have an xy coordinate system and we have a point in that coordinate system, then if we project that point straight down, that gives us the x-coordinate of the point. If we project the point across, we get the y-coordinate of the point, and the point itself is then described by the order pair xp, yp. Well, we can do the same thing in 3 dimensions, but to do that, we first need to be able to sketch a 3-dimensional coordinate system. And basically, the way that goes is we will have an x-axis that comes at a 45-degree angle of inclination towards us, and we're going to sketch that all over here. We're going to sketch a y-axis horizontally that is pointing towards the right, and we're going to sketch a z-axis vertically that is pointing upwards and going through the intersection of the x and the y-axis. And then we're going to scale the axes as appropriate. So basically we have an x-axis coming towards us, we have a y-axis going across, and we have a z-axis going up. And then we can scale those things with equidistant tick marks, just like we have done that also in 2 dimensions, right? And if necessary, we'll also put numbers on those things. And what you can already see is here your brain ought to fill in some of the 3rd dimension, because no matter what I do with this flat screen, I'm not going to be able to pop out a 3rd dimension towards you. But basically, your brain, being accustomed to perspective in drawings, for example, will at some point in time just understand that, yes, okay, this axis isn't just a 45-degree axis. This thing is actually coming towards me, technically out of the plane in which it is drawn, right? And when we draw coordinate axes, interestingly enough, there are right-handed coordinate systems and there are left-handed coordinate systems. And the right-hand rule for the coordinate axes is not an obscene gesture as it may seem, but basically, if you take the thumb of your right hand and assume that that's the x-axis, the index finger of your right hand, and assume that that points in the direction of the y-axis, and the middle finger, that is the part that is problematic in certain cultures, including the American culture, in the middle finger pointing toward in the direction of the z-axis, you basically have those 3 axes of the coordinate system right in your hand. And you will realize that if you did the same thing with your left hand, actually, if you were trying to use your I have to show that to you also. If I were to try to use my left thumb as the x-axis, my left index finger as the y-axis, and the natural way in which my left middle finger would point is not offensive, hopefully, but it is not aligned with the right-handed coordinate system. So a left-handed coordinate system literally is something that is associated with your left hand, and well, you just don't want to squeeze your hand like that to also model that coordinate system with your left hand, right? So that is something to be careful with as we are working with coordinate systems. There are two ways to align the axes, and only one of them is the standard way. All right, so however, independent of left and right hand rules, there are other ways to place the coordinate axes. For example, okay, so this one here basically is a coordinate system that is really nice in that it shows off what we will ultimately call the first octant here. Just as we have quadrants in 2 dimensions, we will have that our 3-dimensional space is cut up into 8 pieces, which are called octants. I'm not quite sure if there's really a canonical numbering, but the one that is bounded by the positive x-axis, the positive y-axis, and the positive z-axis is called the first octant, and that's the one that in this setup stares us right in the face, right? Now, it can also be that we use the same coordinate system, but we have the x-axis going across, the y-axis going up, and the z-axis coming towards us. Setting it up like this is very common as far as I know in physics, and it certainly has an advantage in that we draw the same coordinate system as we have always done, and we just put out a third axis that is coming towards us. And then there is another way of setting things up where the x-axis goes to the right, the y-axis goes into the plane on which things are drawn, and the z-axis is pointing upwards. And again, you can align it with your fingers. It is a right-handed coordinate system, and you can of course put in tick marks just like before. And that is the way in which in my multidimensional calculus classes in Germany we were instructed to draw the axes. And it's something where if you want to visualize it, okay, from the regular coordinate system we've basically took the x and the y-axis and made the y-axis fall down and then put in a z-axis that goes upwards. And the coordinate system that is most customary in the United States would be obtained from this coordinate system by just rotating it around the z-axis until the y-axis goes across and the x-axis comes towards us. And these kinds of mental rotations are certainly one of the next things that you want to be able to do. Here's what I have said before in some presentations. Nobody can put those pictures in your mind. I can show them to you, and I'll be happy to do so, and we'll talk about them, and I'll be probably gushing about them because I find them really cool too. But that is all something that happens on the screen. What I want you to strive for as much as possible to be able to see these pictures in your mind, to at least see the picture that we have right now on your screen in your mind. And when I say, okay, now it rotates around the z-axis, that's something that I want you to be able to see. Every so often I'll be showing you animations and things like that also, but again, that's communication. What happens in your brain is your business, and well, you're the only one who can work on acquiring these things. So, we move on, and well, once we've got coordinates, of course, we want to talk about points. So let's take a look at an XYZ right-handed coordinate system, and we've got the check marks and the tick marks and everything. And if we now put a point in this coordinate system, well, that point just sits there, and we really don't know what the perspective of the point is, right? Is this point behind the plane that is defined by the y-axis and the z-axis? Is it to the left or the right of the plane that is defined by the z-axis and the x-axis? It looks like it's on the right, but there are also ways in which it could be set up where this thing maybe sits in the xy plane way back and is actually to the left of the plane that is defined by the x-axis and the z-axis. And again, these are things that I'm right now just shadowboxing with a mouse with. We will see those planes also, but if you can already see those planes, you've got another leg up on learning multivariable calculus. So here then, in order to draw where the point actually is, we would, if we're just interested in one point, we would just drop a vertical line to the xy plane. And we would then, from the bottom point of that vertical line, draw a line that is parallel to the y-axis going to the z-axis, and a point that would give us the point x, 0, 0. So that would give us the x-coordinate of the point up here. We would also draw a line parallel to the x-axis going towards the y-axis, and that gives us the point 0, y, 0. And well, then this height here will be z, and okay, so this point down here is then the point x, y, and 0, because it's still sitting in the xy plane, and the point up top will be the point x, y, z. So basically the definition is that points in 3 dimensions are given as triples x, y, z of numbers, just as points in 2 dimensions were given as pairs or doubletons of numbers x, y, right? And the coordinates are listed in alphabetical order, x, y, z. So whenever somebody gives you a triple of 3 numbers, you know the first one is the x-coordinate, the second one is the y-coordinate, the third one is the z-coordinate. And yeah, first number is the x-coordinate, second is the y-coordinate, and the third number is the z-coordinate. And the drawing is shown over here. In order to visualize it, you really want to use the x and the y-coordinates to figure out where the bottom point, where the point below this point x, y, z is, the point below this point in 3 dimensions that is just sitting in the xy plane, because that gives you the perspective that shows you exactly where this point ultimately is in space. Okay, so the z-coordinate is the point's height above the plane defined by the x and the y-axis, which is called the xy plane, and that would be this plane here. The x, so that would be the vertical height. The x-coordinate is the point's distance to the plane that is defined by the y and z axis, which is the xy plane, so that would be this plane here, and the x-coordinate tells you how far in front or behind that plane the point is. And the y-coordinate is the point's distance to the plane defined by the x and z axis, which is the xz plane, which is this one here, and so the y-coordinate tells you if you are how far you are to the right or to the left of the xz plane. Okay, so here we have another frame of reference. Typically we will not draw these planes because obviously as soon as you draw these planes you obscure the rest of the picture, and again that is part of the art of visualization here. Okay, so quick simple example, and this is the kind of thing that we could ask you on a homework problem, which looks downright simple, but it's all the stuff in between the lines that you need to internalize. So if we want to sketch the point 2, 3, 4 in 3 dimensions, well, what are we going to do? We sketch an x-axis, a y-axis, a z-axis. We put a scale on the x-axis, on the y-axis, and on the z-axis. And then, well, we know the x-coordinate is 2, and we know that the y-coordinate is 3. And so now if we go across and up to the x-axis, we know that this point here is 2, 3, 0. And from this point, we're going 4 steps up, and here's where we just have to realize that, okay, this 0 is this 0 here, and this top here is aligned with that 4. So we just measure 4 on the z-axis and transfer that over here. We don't go all the way to that 4, right? We don't go all the way up here. And that would be the height z equals 4, and then the point is up here, and that's the point 2, 3, 4. And that's already all we can do in terms of sketching one point. However, we've got to be careful, as I mentioned, we've got to be careful with perspective. So if we're looking at this picture, as long as we have these lines that give us the perspective, we see, yeah, this ought to be the point 2, 3, 4. But if we look at the same thing and we just have the point, then all of a sudden we realize that, well, this point could have projected down into the xy plane only up to over here, and then projected across to the x-axis and down to the y-axis, and all of a sudden that very same picture of that very same point could have also been the point x equals -1. Well, right, -1. Y equals 0.9 here, and then this height I measured out, and it looked to be about 2, about this height here. So this is something that in 3-dimensional visualizations can be challenging, because if we were to plot these 2 points in the same graph, then this point here would be behind this point here, just as we are going to see hidden lines and various, or we're going to have hidden lines and various other things as we draw pictures of equations, or for example spheres, which ought to be next. So proposition, well, we first, in order to determine what a sphere is, we need a distance formula, and here's where we're also going to have a proof that is going to be another exercise in visualization and digging things out from single variable calculus. If I'm interested in the distance from the point x1, y1, z1 to the point x2, y2, z2, well, that is given by the distance formula, and that distance is the square root x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So it's very much like the distance formula in 2 dimensions, which would only use these two different squares of differences and then take the square root. It's just that in 3 coordinates, in 3 dimensions, we have that third coordinate in there also. So it ought to be easy to memorize. And even though I'm often saying there are things that are not worth memorizing, this formula needs to be committed to memory. The other question that we should ask ourselves, however, is why is this formula true? Now, I will often say calculus is not a proof class, but calculus is about understanding, mathematics is about understanding, and it's about justifying. And here we can put that together with a really neat visualization task. So let us take a look at the proof for the distance formula, which will also show why I split this up like this. I have enough room to put the picture here. So we have a right-handed XYZ coordinate system, right? For three-dimensional visualization, at some point in time, that's got to be a reflex. When you visualize in 3 dimensions, first thing you do is you get yourself those 3 axes in your mind. Okay, now I've got one point here, that's x1, y1, z1. I've got another point here, x2, y2, z2, and what I'm interested in is this distance. Well, in order to figure out this distance, I first have to give myself here a little bit of perspective, right? So I'm projecting the 2 points down into the xy plane. Now the xy plane is nice because in the xy plane I can measure this distance. Because I have the distance formula from 2 dimensions, or I've got Pythagoras law if I want to go way back to trigonometry. Because if I look at this line here, well, if I project it across, first coordinate, second coordinate, well, then this one, I think this one here is the first one that I'm showing. Well, okay, this distance is x2 minus x1, and that is because this coordinate here is x2, this coordinate here is x1, so the distance is the absolute value of x2 minus x1. I'm putting in the absolute value because I don't want to mess with negative signs here. And so then this distance over here, well, that'll give me y1 here and y2 here, so this distance will be the y2 minus y1. Okay, here the y2 actually is bigger, so I didn't throw in an absolute value sign. But what we can then see here, if we see the perspective correctly, we realize this is a right triangle, right? Because no matter how we draw these things to give our brain the impression of perspective, this angle between the x and the y-axis is a right angle. And this angle is the same kind of angle, so that's a right angle also. So what I have here is a triangle where we've got a right angle here. This line has length x2 minus x1 absolute value. This line here has length y2 minus y1 absolute value, which means by Pythagoras law, this is this length squared plus this length squared, and then we take the square root. So this is square root x2 minus x1 squared plus y2 minus y1 quantity squared, and we take the square root of the whole thing. Okay, now this length, of course, is only related to this distance here. But if we push this length up, and we can't do that, right? If I take this line and just move it up, the length of the line doesn't change. Well, then all of a sudden I get another triangle where I've got 3 points here, and this point is the point. Well, which point should that be? That should be x2, y2, because it's below this point here, and it's at height z1 because it's at the same height at this triple z1 here, right? Again, we can see here this is a 2-dimensional picture. Your brain has to fill in the 3-dimensional aspect that says that, okay, these two are at the same height z1, and this one is underneath the point x2, y2, z2, which means that the first 2 coordinates are x2 and y2. Either way, well, now we've got this. So now we have a line in the xy plane and a line that is parallel to the z-axis, which means, again, we have a right angle here. And because we have a right angle here, we know that this length here can be obtained with Pythagoras law from this length, which we have here, and the length of this vertical line here, which is, of course, just z2 minus z1. And so that means that, again, by Pythagoras law, put into 3 dimensions, we have that this is square root of the length of this dashed side here, which is the square of square root x2 minus x1 squared plus y2 minus y1 squared, quantity squared, plus the length of this line here, and that's z2 minus z1 squared. And of course, after you have cancelled the square root and the square, you get exactly this picture down here. And so here's where you can already see how this kind of stuff can work. The next example is a typical homework problem. Compute the distance between 2 points. It's going to be trivial. You just plug in things into the formula and that's it. But what you want to internalize is you want to internalize pictures like this one, because pictures like this one are ultimately what is going to get you through the various modeling aspects that will allow you to turn tasks about modeling volumes, tasks about modeling things on spiral paths and various other things. These kinds of visualizations will allow you to turn these pictures into formulas that then can be digested with the computations of calculus. Now let's take a look at something that we should have a hearty laugh at, because first example here, this is probably also something that you're going to see in a homework problem. Compute the distance between the points a equals 2, 5, negative 3, and b equals negative 1, 3, negative 1. Well, what are we going to do? The distance between these 2 points is computed with the distance formula. So you take first coordinate of the first minus first coordinate of the second, second coordinate of the first minus second coordinate of the second, third coordinate of the first minus third coordinate of the second. You take those differences, you square them, you add them up, and you take the square root. Need to make sure that you deal correctly with the negative signs, and so we end up with 2 minus negative 1 is 3, quantity squared, 5 minus 3, 2 squared, and negative 3 minus negative 1 is negative 2, and of course the negative sign doesn't matter, so we get 2 squared here, square root of 9 plus 4, which is square root of 17, and that's it. So don't be blindsided by stuff like this being terribly easy. Of course, you've got to be able to do it, but there's a whole lot more underneath that you want to start internalizing, even if it isn't directly assessed. Okay, now we're actually going to talk about spheres, right? And so the first thing, how do you draw a sphere? Well, you draw the center, you draw a circle, then you give yourself a little bit of perspective to see that the sphere is coming at you. You give yourself a dashed line or dotted line in the end that says, yeah, okay, this line we don't see, but that's the part of the sphere that we don't see. And then you give yourself a line towards the front that tells you, yeah, the sphere is also coming out towards you in the vertical direction. And you give yourself a dotted or dashed line in the back that gives you also the third dimension of the sphere behind it. And then, well, you can see that, of course, the idea for a sphere is the sphere is the set of all points that are a fixed radius away from the center, which is exactly what the definition of a sphere is. A sphere is a set of all points x, y, z that are a certain distance r, the radius, from a given center point a, b, c. And what that means then is that the equation of a sphere with center a, b, c and radius r is, well, let's see, the distance would be, if a point on the sphere has coordinates x, y, z, the distance from the center would be the square root of x minus a quantity squared plus y minus b quantity squared plus z minus c quantity squared. And so the square root of this stuff ought to be r for every point on the sphere. And basically, because we don't want to carry around the square root, we just go ahead and square both sides of the equation that we would get from the distance formula. And so we get just distance squared equals radius squared here. All right, so what we can do then is we can find center and radius of a sphere given by a certain equation. And that, well, that looks quite horrible, right? We've got x squared plus y squared plus z squared plus 2x minus 8y minus 6z plus 1. And so now we are delving into some of the computational aspects of multivariable calculus. We just need to puzzle this apart and realize that as we look at this equation, we want to separate x, y, and z coordinates as much as we can, because that will give us an idea what this thing looks like. Because right now, I'm just telling you that that is a sphere. You have no reason to believe that. You just have an equation, right? So one of the ways to handle equations like these is that we're looking first at all the stuff in x, so that that's x squared plus 2x. Well, the equation of a sphere doesn't have linear terms in x, but we know we can get rid of those things by completing the square. And so I can look at x squared plus 2x, the term that completes the square is 1, and I'm going to just subtract the 1 in the same breath, so I'm just not changing anything. Basically, I have added 0. I could have also added things on the right-hand side that would have been a little bit harder in terms of the animations that I'm setting up here, but more importantly, actually, you really want to get used to this trick of adding and subtracting 0, or adding and subtracting the same number, because that is something that every so often in these nasty computations comes in very, very handily. So you can already predict the next one. We're looking for y squared. We're looking for the negative 8y. And the term that completes the square would be half of this one here squared. So that would be 16. And I'm subtracting 16 right away. So again, I have only added 0. I have not changed the problem. Then I'm looking for the stuff that goes with z. Well, we've got z squared. We've got negative 6z. The term that completes the square is 9. And I'm subtracting the 9 off. And so now we have digested all these terms here, which is good. What remains is the plus 1. Of course, we copy the plus 1. The right side is still equal to 0. And now we realize that this one here is, well, these three terms are x plus 1 squared. These three terms here are y minus 4 squared, right? And then these three terms here are z minus 3 quantity squared. Z minus 3 quantity squared. And then we just add the numbers. Let's see. And so now, of course, the negative numbers are what's left here. Minus 1 minus 9 is negative 10. Minus 16 is negative 26. Plus 1 is minus 25. And then, of course, the right-hand side is 0. And if we put the 25 over to the right-hand side, we realize this is a sphere. This is the equation of a sphere. The center is, the z-coordinate is 3. The y-coordinate is 4, easily readable. But because the equation of the sphere has a minus in here, sort of like how the quadratic formula has pluses, and when you've got minuses, you have to explicitly digest them. Well, this plus has to become a minus minus, and so the x-coordinate of the center is negative 1. And of course, the radius is 5. You have to take the square root of the right-hand side, because the right-hand side is r squared. Now, that is probably not too hard, but again, we're seeing a couple of things here. Among them is that as we are doing multivariable calculus, at some point in time, we just need to dig stuff out from the past, even if it's a year ago since last we completed a square in a pre-calculus algebra class or so. And the thing with this kind of thing is not to get frustrated if you don't remember. And worst case scenario, of course, you have to look things up, but try to drag these things out of your memory, because as you drag them out of your memory, especially when you are correct, you make the right kind of mental connection so that these things will come more naturally to you as you proceed. And that's what you want. You don't want to cram before an exam. You just want to sit there and realize, yes, I can do all the things that are necessary, and then get a good night's sleep. Because come on, do you need to practice completing the square? You need a little bit more organization maybe, because we've got an extra variable here. But that kind of bookkeeping also comes with the practice we're getting here. All right, we move on. And well, technically, I've already told you about equations, but spheres are something that is very natural. If we're looking at the graph of an equation in 3 variables x, y, z, it's basically the set of all triples u, v, w in 3-dimensional space, which lead to a true statement when u is substituted in for x, v is substituted for y, and w is substituted for z. And if we're looking at that, this is, and this is something that you probably would want to look up, and it's useful. This is the same definition as for the graph of an equation in 2 variables way back when we last did it, maybe early on in calculus, or maybe even before then in algebra. We've just gotten so used to graphs being x, f of x or so, to not realize that those are actually pairs, or to not consciously remember anymore that those are pairs x, y, so that the equation y equals f of x is satisfied. Nonetheless, it is the same thing, only with a third coordinate thrown in. So the only thing that changes is that this time we have one more variable. So if we're looking at that, well, ABC is the center of a sphere. The blue ones here, that's all the points that satisfy the equation of the sphere. Here's the radius. And the equation, of course, is basically this blue picture. This geometric object is the set of all points x, y, z, so that the coordinates x, y, z satisfy this equation. That sounds like much ado about very little, and it is, but I want you to internalize that, because this is the kind of thing that we will be defaulting to throughout the course. All right, so simple example. Let's describe the shape of the surface x squared plus y squared equals 1 in three-dimensional space. And what I typically get in any class of multivariable calculus that I teach at this stage is when I say, what does x squared plus y squared equals 1 describe? Everybody will say, hey, I know that that's a circle. That's a reflex. And it's not a bad reflex, because if we're looking at an xyz coordinate system, x squared plus y squared equals 1 would describe a circle if it wasn't for that third dimension. And so basically the rule is, remember that the graph of an equation is the set of all points x, y, z that satisfy this equation. And so because there is no z coordinate in this equation, I can make my z arbitrary. So basically, not just this circle in the xy plane satisfies the, or is the graph of the equation x squared plus y squared equals 1 in 3 dimensions, but it actually is also all the circles that I can find above and below it. So if I move a circle up and down the z-axis, what I get is something of a cylindrical object. And I'm also changing color here, because even though there is no law that says surfaces in 3 dimensions must be blue, there typically will be in this course, just to distinguish them from other things that we may have to draw into the same picture. Of course, if I have several surfaces, I will use different colors, as you already have seen in the picture of the coordinate planes. But basically what you've got to remember here is that if a coordinate is missing, then the shape that you are very familiar with from two-dimensional geometry actually will be continued in the third direction, which is the z-axis. So this is a cylinder that actually goes indefinitely up as well as indefinitely down. It's an infinite cylinder surrounding the z-axis. And again here, the kind of thing that you want to be able to do is ultimately when somebody says, I'm talking about a cylinder, your mental eye, it would be really nice if before your mental eye you could see a picture like this that just says, yeah, okay, there's a cylinder. And this kind of shadow boxing that I'm doing right now is very much what people do when they talk about multivariable calculus. And ultimately, if that doesn't work, or when that doesn't work, you want to be able to draw a picture, and we'll talk a little bit about the value of drawing pictures also in this presentation. All right, so that's already it here, right? Describe the shape. It's a cylinder. Okay, I should have probably typed here, it's a cylinder, end of story. Well, okay, you can see that here too. If we're looking at something more complicated, such as the graph of the equation z squared equals x squared plus y squared, well, that gets a little bit harder, because now we have all 3 coordinates, right? And so now there are different ways to think about that. Let me first show you how I've drawn it. Okay, again, the reflex, we're talking about 3 dimensions. We've got to draw a 3-dimensional coordinate system. X-axis, Y-axis, Z-axis, make sure it's a right-handed coordinate system. We're looking at x squared plus y squared equals z squared. And one way to think about that, which we will also look at in more detail later, is that x squared plus y squared could be the distance away from the x-axis, right? That's what it was for the radius of that cylinder in the previous example. So basically, this equation just tells me that the square of the radius is z squared, the radius is z. So basically, and this is another way of thinking about this, is you could have said x squared plus y squared equals something is the equation of a circle, and the radius of the circle is z, and the z squared just tells you how high that circle has to be placed above the xy plane. Either way, what you get is r equals z is a straight line, also over here, and then the circles basically tell you that this is a straight line that rotates around the z-axis. So it's a cylindrically symmetric object. Similarly, the lines, of course, also go below the z-axis, because the square eradicate any concern about negative signs. So we also have circles below the z-axis, and what we have here then is the picture of a cone. Okay, so I could have again said at the bottom here, this is the picture of a cone. Cones are another set of standard objects that we are going to work with. So again, when we will talk about cones, it will be really helpful if before your mental eye you could see a picture like the one we have here, and that really is the challenge. What am I telling you here? I'm telling you something that I can check. I'm saying make this picture appear in your mind. I hope you can do it. Otherwise, you can also work things with computer algebra systems. There are wonderful visualization tools out there, but as much as possible, you want to have these pictures in your mind. Okay, so now should come, I mean, even though this presentation already sounds like a sermon, here's another part to the sermon. Don't panic. We'll revisit visualization and drawing skills several times in the early part of multivariable calculus and even after that also. So if you're sitting right now at this thinking, man, I really have a hard time drawing this stuff. Oh boy, I can see the 2 dimensions, I can't see the 3rd dimension. If you have trouble like that, that is downright normal, right? What did I say? Multivariable calculus is easy as long as you can see the pictures and the computations don't bother you. And if that was easy for everybody, everybody would have breezed already through through single variable calculus. And that was already pretty hard. So the thing that we're going to do is we're going to use these skills in context, and that will sharpen them further. So we will get better, and this will feel more natural soon, but visualization will always be challenging. So as we go through this, if you are using a computer algebra system to check yourself, by all means do so. Learn how to use a computer algebra system to do 3-dimensional visualizations. That is something that I'll probably also present in my face-to-face classes. I'm not going to connect these presentations too much to one computer algebra system. I will show you pictures that I'm creating with MathCAD, but this is all about calculus. It's not about a specific piece of software. So it will always remain challenging, and that is because visual recognition is challenging by nature. Remember, when every so often when you open an online account, you've got these little questions that say, type the letters in this picture, and then you've got, I don't know, bubbles and colors, and in those letters there is a phrase like, how you doing, or something like that, and you're supposed to type that in, and you often wonder, well, what kind of a fool would not be able to do that? And the thing is, these kinds of things are safeguards against automatic creation of accounts. They are safeguards against automatic hacking, and that is because you can read the letters in these pictures, and a computer cannot identify them if they are sufficiently distorted. And the reason for that is because you have a visual cortex and a brain, and a computer does not. And so that also means that unlike a lot of computation, exactly these visual skills, which feed directly into modeling, which feed directly into scientific invention and the like, these skills cannot be automatized. And I'm putting a yet behind that because, of course, there are very smart people working on computer vision, computer visualization, and so on, because it can help greatly in automatic face recognition if you're looking at tracking criminals, for example. And so it is something that if you're interested in, there is an industry out there that will happily receive smart people who can make contributions towards that. At the same time, my own feeling is that this is a genuinely human task, and so even though we can make this better, it's probably going to be a while, and it may never happen that the recognition will be as good as what happens with a human brain. And well, that is kind of nice, because that means there is still a place for human brains in all these things that we are doing here. So, take the drawing seriously, for example, and that is, chances are you will have a computer and drawing programs available for your job. I mean, everything that I'm doing here is done with a drawing program, and yet I first cut my teeth on drawing these things by hand. I first had to draw it by hand and see it in my mind. Ultimately, I've gotten to the point where I can draw them directly into the computer, but that is a similar skill. It's still drawing. Whether I've got a computer that makes my lines straight or not doesn't really matter that much. And so you may even have a graphic artist working for you. Neither your computer nor your graphic artist can read your mind, and so as you quickly describe a picture, the best way to do that is with a quick sketch, and you can do that by hand or with a computer-aided design program. But certainly, especially at first, hand sketches probably work better than also dealing with the vagaries of a piece of software. Alright, so now let's take a quick look at the comparison between 2 dimensions and 3 dimensions, right? 2 dimensions are what we are very comfortable with. We've done 2-dimensional stuff for about a year's worth of single variable calculus. We need to pop that 3rd dimension in there. So points x, y in 2-dimensional space can be embedded into 3-dimensional space as triples x, y, 0. So similarly, we can embed a two-dimensional object into three-dimensional space by placing it into the xy plane of three-dimensional space. That is a trick that for the geometric aspect is very simple, right? You've got x, y, z, right-handed coordinate system. I can place a circle in 2 dimensions, into 3 dimensions also. I would just have to say that this is x squared plus y squared equals 1 and z equals 0. All of a sudden, x squared plus y squared equals 1 does not describe a cylinder anymore because I'm putting an added constraint on there. I'm saying this thing is sitting in the xy plane. And so this trick is going to be very helpful as we are dealing with formulas, because we will be able to economize on memorizing formulas. We will, or I would typically recommend that you memorize formulas for three-dimensional space. And if people want to talk about two-dimensional space, well, you just know that the third coordinate is 0. How hard can it be to stick a 0 into those formulas, right? If we're looking at the analytical aspect, well, the distance between the points x1, y1 and x2, y2, that's a distance formula that we know from working with two-dimensional objects. We realize that that's the same as the distance between the points x1, y1, 0 and x2, y2, 0, because that's the same xy plane, right? It's now just placed in three dimensions. And so that means that distance formula in 3 dimensions is square root x2 minus x1 quantity squared plus y2 minus y1 quantity squared plus 0 minus 0 squared, which is exactly the formula that you have memorized all along. And so that means that a lot of what we're doing here can be very helpful if and when, or it can be easier to learn when you connect it to stuff that you know already, and to realize that really all we're doing is we're tacking on another coordinate. And then what can be really helpful is to make the 3 dimensions your natural environment. That will save you, that can save you a lot of grief as you are going through physics, for example, when you have to do 3-dimensional modeling, because you don't have to worry anymore about your x and y coordinates. You just know everything is worked out in 3 dimensions. You just remember the 3-dimensional formulas and therefore don't have clutter in your mind with 2-dimensional formulas. Now, that is not going to make that much sense right now, but I will, in these presentations, very much beat that drum to say, look, we memorize this stuff in 3 dimensions, and if you need a formula for 2 dimensions, we will use tricks like these to use visualization and computation that we need to practice anyway, rather than memorizing 3 formulas where 1 will suffice. We will see that as we go through the course. All right, so the other thing that happens is we can model even more complicated scenarios. For example, we can model space-time, which would be 3 space coordinates and a time coordinate. And so basically, for our purposes right now, that's basically a movie. That's a 3-dimensional picture that moves, right? Because a 3-dimensional picture gives you the coordinates of the objects that you're interested in, and the movie then tracks just how these objects move over time. Space-time, of course, is typically connected to the theory of relativity in physics, but technically speaking, if we are visualizing something that evolves in time in 3-dimensional space, we're also looking at space-time. It's just space-time at non-relativistic speeds. We can visualize phase space, which is something that you can use to keep track of 3 space coordinates and 3 velocity coordinates. Of course, for that, we have to think about what velocities actually are, and we will talk about vectors in the next presentation. And fortunately, I mean, I'm talking here about stuff that has 4 dimensions. I'm talking here about stuff that has 6 dimensions. I'm talking about stuff that sounds like it's terrible to visualize. And personally, I also have to freely admit without shame, I don't know how to visualize phase space. I haven't worked with it enough, but I'm not sure I'll ever be able to put 6 dimensions into this small brain of mine. And the fortunate thing is that the formal aspects do not change much, because if we're looking at a point in n-dimensional space, so if we're going to go all the way to the abstraction that typically is only done in a mathematics class at an upper level, when we talk about n-dimensional space and advanced calculus, let's say, well, a point in n-dimensional space is just an n-tuple of numbers x1 through xn. So as long as we are on top of all the formal aspects, if we need to describe something with 11 dimensions, it's just 11 numbers. So what? We write them down, we deal with them. When we're looking, therefore, for example, at things like the distance, and the distance is, of course, a very visual notions, the distance between 2 points. I can see it in 2 dimensions, I can see it in 3 dimensions. I possibly can fake it in 4 dimensions. In dimensions, the pictures I see, I'll freely admit that they're 2-dimensional, they're 3-dimensional. I can't see in dimensions. And if somebody, maybe some of my smarter colleagues, scoff at me for that, so be it. Maybe you just can stick more dimensions in your brain. But what happens is the formal aspects stay the same. The distance from one point in n-dimensional space to another point in n-dimensional space, you've got 3 guesses what it is. It's the square root of the sum of the squared differences between the coordinates. y1 minus x1 quantity squared, y2 minus x2 quantity squared, all the way through yn minus xn quantity squared. Then you take the square root. The proof is also very similar, because you would keep on projecting things, you would keep on setting up triangles in higher and higher dimensions and keep using the law of Pythagoras, just like we did in the presentation of the proof of the distance formula in 3 dimensions. And so here's where we are at this juncture, where hopefully you're not getting too worried, because I'm going to bang the drum of looking at things in n dimensions for a while also. The visualizations typically are 2-dimensional and 3-dimensional. However, working at it in n dimensions will help us, because we won't have to memorize a formula for 2 dimensions, a formula for 3 dimensions, and oh my god, there's a formula for n dimensions also. Look, if you've got the formula for n dimensions, for the distance formula, for example, you've got it for all dimensions. If I stick in n equals 2, I've got the distance formula that we already know. If I stick in n equals 3, we've got the distance formula that we've got for 3 dimensions that we've just introduced here, and so on, and so on. And so in some ways, you're going to be hopefully disappointed by the homework assignments for this section, because there isn't much we can do at this stage. We can work with equations of spheres, we can let you graph some equations, we can let you compute distances between points. None of that should be too bad, but as you are doing these things, you want to work the visualizations, you want to remember the formulas, you want to get yourself into the frame of mind of thinking in multiple dimensions. And of course, we're going to keep doing that for the remaining presentations in the multivariable part of this course. That's not a threat. It's also not a promise. It's simply a fact. It's something that we have to do. I hope you'll enjoy it as much as I do. You can see me already doing the shadow boxing, talking about cylinders, talking about cones and things like that. That's the kind of thing that you need to see in front of your mental eye to just really have smooth sailing. If that's a little bit hard, hey, it's natural. All right, I'll see you for vectors.